Welcome. In this lecture, we will discuss the coke rate and fuel efficiency in blast furnace, because coke rate is also to some extent is correlated because very much associated with the aerodynamics. So after studying the aerodynamics, I am studying that is why the coke rate and the fuel efficiency in blast furnace. So, what are the factors? There is a concept that will be covered, are the factors on which the coke rate or the fuel rate in the blast furnace depends, and the various blast additives like PCI, oxygen enrichment, steam and oil. I will basically discuss the oxygen enrichment in the next lecture. Okay. Now, so typical cost breakup for the hot metal. If you see, if you want to produce hot metal, what is the cost breakup? From this pie diagram you can see there is the 50%, around 50% of the cost of the hot metal is contributed by the cost of the coke. There is the cost of the coke is the major part of the iron making, because the coke is made from a special grade of coal called the coking coal, and the coking coal is very scarce. Only in the world, very few places are there where the coking coal reserves is there. In India is a very rare, and only in the Raniganj and Jharia area you have certain amount of coking coal. Most of the coking coal is imported from Australia. Okay, so that's why the cost is very high, and coking coal is very costly. That's why, and besides, that's why there is always people are trying how to reduce the coke rate in the blast furnace. But blast furnace cannot operate with a minimum amount of coke. A certain amount of coke is required basically to physically hold the overburden in the blast furnace. So, coke is essential, but obviously the coke rate can be reduced. How you can reduce the coke rate? Because if you can supplement the two major function of the coke, that is the heat generation and your reduction potential of the gas. If you can give the reduction potential as well as the heat, supplement the heat of the coke that is obtained from the coke, then to some extent you can reduce the coke rate. But third function of the coke is to hold the overburden, for which a minimum amount of coke is required. But anyway, so initially the blast furnace used to operate with 700, 800, even 1000 that is the 1 ton of coke per ton of iron produced long before, and after that it has decreased significantly, and today the coke rate is only say the 350 kg per ton of hot metal. So, and obviously the reduced, if you can reduce the coke rate in the blast furnace, you can increase the productivity, because in productivity definition I said P is equal to Q by K, K is in the denominator. So, if you can reduce the coke, basically if you reduce the coke, basically you are making some space for the iron ore. So, your productivity obviously will be more, right. So, now it is you can see some developments in the blast furnace iron making. Then there is the iron ore beneficiation. Previous days, what was first done is basically iron ore beneficiation, use of basically overseas rich iron. Those were the thing, because the blast furnace, as I say, it is very sensitive to the raw material, and the raw material quality has to be good. Basically it should have sufficient strength, and abrasion resistant, impact strength should be high, such that when they are passing through this, when the burden is moving from the top to the bottom, they do not generate much of fines, because fines produces a lot of phenomena, like all these irregularities is coming from the fines only. So, that is why the iron ore beneficiation and overseas rich ore, those were the initial thing, because and then use of iron ore flakes, because all the country do not have the rich iron ore, they have to import it from outside country, because blast furnace cannot operate with a very good raw material. Now, then use of iron ore pellets, and then the fine agglomeration in the form of pellets, but that is a very costly process, that is why. But pellets started into the blast furnace, because pellet charge furnace is very its permeability gives a wonderful permeability of the bed. So, pellet is a very good feed material, but it is very costly. That is why sinter got an edge over pellets, although pellets are better than sinter to some extent, that is for the bed permeability is concerned. Then oil injection, that is the auxiliary oil injection came into the blast furnace. This oil injection basically, why? Because it was an idea that is it can increase the productivity, because oil basically can supplement the heat and the reduction potential of the coke that is obtained from the coke. So you can reduce the coke rate, and if you can reduce the coke rate, your productivity increase. That is why oil injection came only to increase the productivity. Not only productivity, oil injection also can increase the indirect reduction, because oil is a hydrocarbon, it gives hydrogen also, and hydrogen is a better reductant than coke, than the CO gas. So as a result, it promotes the indirect reduction. So oil injection, it can increase the indirect reduction, and then it can increase the productivity and efficiency of the furnace. And hydrogen is a better reductant than CO for chemical efficiency also concerned. There is the H2 utilization is better than CO utilization, especially at the high temperature, as we have seen. So oil injection came, and then your blast temperature, because if you increase the blast temperature also, then also you can supplement the heat that is provided by the coke, and you can reduce the coke rate. Then top counter pressure, beltless charge, beltless top charging, and then you have the top pressure. If you have a top pressure, then you can produce more, because you can use more blast rate without increasing the pressure drop, if you can increase the high top pressure. So that was came, and then improvement of the iron burden properties, that is impact property, strength, just by agglomeration. Different agglomeration technique came. There is the sintering, and then pelletization. So and then also you can improve the burden properties by proper beneficiation. You can make the ore rich in iron. So and then I will come to that, all these things, and then improvement of the coke properties also came, and then came the coal injection, because the initially it was oil injection only to increase the productivity and the efficiency, to increase the efficiency. Oil first came in around before the World War II. That was the only oil injection was the additive, only that was the only additives through the blast. After the World War II, because of oil crisis came, and then the year that is the Iran-Iraq were also there in 1970s, late 1970s. So in the 1970s, everything happened. That is the so because of that, what happens? Your that is coal injection come into picture, because oil price was increasing too much. So because of oil price, the people thought about why not charge the pulverized coal, pulverized non-coking coal, why not charge into the blast furnace? It can also supplement the coke. So then came the coal injection. Basically, it was the first coke injection plant came in Japan, I think in 1981. And after that, it is steadily increasing. Nowadays, most of the plants are equipped with the pulverized PCI injection, pulverized coal injection, and nowadays the benchmark is 200 kg per ton of hot metals. So 200 kg of PCI is charged along with 350 kg of coke, around 550 is that thing total coal charging. And then came, there is the coal injection, then the copper step cooling of the blast furnace, such that the campaign line greater than 15. If you do the copper, there is the refractory lining. That is another problem to stop the blast furnace get suddenly stop, because the refractory, if you don't look after the refractory, then you have to stop the blast furnace. So that's why the refractory cooling came using the copper step, and then campaign line become greater than 15 years. So 15 years continuously you can work and don't have to do. Then this is the basically what is the improvement has come, and most of the development are related to the auxiliary injection in aerodynamics and the fuel efficiency. That's why I have combined this aerodynamics along with this fuel efficiency. And the coal injection become very, that's why I say that is the coal injection basically came after the, there is the oil crisis, two oil crises that we faced. Okay. Now the factor affecting the coke rate, one is the obviously what are the factors that that is the thing. One thing is the burden quality, that is the charge material. Okay. And because the burden quality is basically the gangue. The burden should not have much of gangue, because if it is a lot of gangue, it will, the slag volume produced will be high, chances of flooding will be more. And the strength is very important, so that if strength is high, it will not generate the fines and the dry zone will remain good. And if your gangue is less, then your wet zone will remain good. So burden quality has to be, if you look for the burden quality, your coke rate can be easily reduced. Then burden distribution, how we are distributing the burden, basically that is the evolution of the your gas flow dynamics through the bed basically depends on, to some extent, on the burden distribution also, how we are charging the burden such that the across the cross section the permeability remain almost uniform. Okay. So, burden distribution has a role to play. If you have permeability is better, then your coke utilization is better, your coke rate will be reduced. Then blast additive, obviously blast additive, all the blast additive basically you can replace a certain amount of coke by the blast additive like pulverized coal injection, oil injection, steam injection, and oxygen enrichment is basically to support this auxiliary fuel injection, and blast preheating also can reduce the coke rate. Obviously, you are giving some sensible heat to the blast preheat, so you can do that thing. And the replacement ratio, you can see there is the kg of coke shipped. It is defined as replacement ratio is the kg of coke shipped per kg of additives that you charge, and you can find some of the replacement ratio. There is the, for coal it is 0.9. Obviously, it is for a high rank coal, because if the rank of the coal, the fixed carbon is less, replacement ratio is not that much. So, PCI replacement ratio is 0.9 for a high rank coal. Low rank coal do not give that much of replacement ratio. Similarly, natural gas 1.25, oil also has 1.1, and tar is 1. Okay. Now, oil injection. Oil injection, what happens? It decreases the coke rate and increase the productivity obviously, and generate more volume of blast furnace gas. That is the thing. That per kg of carbon if you burn, you can get 5.376. That is the normal meter cube of gas, but if you burn 1 kg of oil, you can get 5.86 normal meter cube of the gas. So, it generates more volume compared to carbon. So, blast furnace gas heat capacity increases, because more volume means more heat capacity, but reduces the flame temperature, because more volume generate, and it also basically it also generate less amount of heat, because you can see it generates 1466 kilocalorie compared to 2300 kilocalorie if you burn 1 kg of carbon. So, it generates much less heat. As a result, it decreases the flame temperature. If the flame temperature is less, then your heat exchange, what is that? That is the potential, that is the heat exchange potential of the gas also become less, because less temperature gradient is less, is heat potential is also less, but it increases the heat capacity of the gas, more volume of the gas. So, heat content become more, but its potential become less. So, as a result, your isothermal zone shrinks to allow more furnace volume for the heat exchange, because this volume of the gas is high. So, you have to allow more furnace volume for the heat exchange between solid and gas. As a result, your isothermal zone gets shrink. Okay. So, that is the thing, and obviously, you cannot isothermal zone, if you just go on increasing the oil injection, isothermal zone shrink, and if isothermal zone finally evaporates from the system, then you cannot maintain a distinct heat balance in the lower part and upper part of the furnace. That will be a problem. Okay. So, thing is there. That is why if you do too much of oil injection, then you have to supplement it by oxygen enrichment, usually accompanied with the oxygen enrichment. Why oxygen enrichment? If you do the oxygen enrichment, what you are doing basically, you are replacing some amount of nitrogen by oxygen. So, air blast volume decreases. As the volume decreases, and also what is that, with the less air volume you can generate the same amount of heat, you are burning the same amount of carbon, because the oxygen is more in the air blast. So, as a result, what happens, raft increases, adiabatic, there is the raceway adiabatic flame temperature, that is the thing that increases, but its heat capacity decreases. So, basically in case of the oil injection, the reverse phenomena take place, raft decreases and the heat capacity increases. So, if you can supplement these two, that is, if you use the oil injection, do some amount of oxygen enrichment, then the decrease in shaft, decrease in raft by what is that, your oil injection can be compensated by the oxygen enrichment. Similarly, increase in the heat capacity of the gas or decrease in heat capacity of the gas by oxygen enrichment can be compensated by increase in heat capacity of gas by oil injection. So, that is why they are basically complementary each other. So, you have to do both the things. And oil injection provides hydrogen, which is good for efficient indirect reduction. Direct reduction take place in the blast furnace. And one thing very important, that is the direct reduction in the blast furnace eventually take place, because lower part the temperature is very high and carbon is there. So, direct reduction eventually take place, but think is that indirect reduction, that you have to increase the indirect reduction in the blast furnace, because in the dry zone gas moves very fast and the residence time and interaction is not very high. So, and in that case the indirect reduction, because and also the permeability, bed permeability is a question. So, if you do not have bed permeability, so you have to increase the gas and the solid interaction too much for the indirect reduction. So, and also if you can replace some amount of the CO by hydrogen, hydrogen is a better reductant, yes, thermodynamically as well as kinetically. So, in that case your indirect reduction can increase. That is why oil injection is better, because it provides the hydrogen. So, now next we come the PCI, because nowadays it is not oil injection anymore, because of oil prices increases, and then people have shifted to the PCI, and the PCI today is the major blast additive, you can say. And its replacement ratio, as I said, basically if it is the rank of the coal is very high, it can be 0.9, but it can be as low as 0.6 also, depending on the rank of the coal. So, Armco first installed such machine in Oita, Japan in 1981, and this is the schematics, that is the how it is done. Basically you can see this is the raw coal burden, the bunker is there, here is the coal are stored, and then they go to the pulverizer, it is pulverized here. After that you have to air dryer, there is the air heater is there, because the coal has to be dried up, because if it is not dried up then its flowability will be less, and also it will add to the endothermic reduction, endothermic reaction. So, basically the pulverizer is there, after pulverizing you have to dry it completely, and once it is dried then you take it to the cyclone, hydrocyclone separator, because this cyclone separator is required to take out the fines, which is the powdery mass, because the powdery mass basically also reduces the flowability of the coal PCI, but its size has to be low such that it burns in the ratio also. Size has to be low, but too low size or the powdery size is also not good for your flowability point of view. That is why it is taken to the cyclone, and in the hydrocyclone you take out the fines and in a back filter, and then the undersides come up here, and this is the reservoir tank, and from here you can find there are basically feed tanks are there, these are the 3 feed tanks, and then your compressed nitrogen you are passing as a carrier gas, because you have to because coal you cannot charge through the nozzle, because if you want to pass through a pipe you have to have some kind of carrier gas. So, basically nitrogen and air is used as a carrier gas to pass it through the distributor, and then basically loading ratio here it is decided how much solid to the gas, and then after that you pass it through the what is that called, our tuer. Now, you can see it is the bigger form it is given here. This is with injection lens, it comes from the side and enters into the tuer. You can see what air blast is coming, preheated air blast, and it is mixed up here, and here it is charged. This is the pulverized PCI, and then it carried, and then it comes with the hot gas, it comes here, and then it burns here. Okay. Today most of the furnace achieved 200 PCI, that is thing. The salient features of the PCI injection. So, Ghosh and Chatterjee book, it is written like this very nicely. What are the salient features? First thing is that steps in PCI combustion. What are the steps PCI? One thing is that heating, that is, and then because whatever you just take out the moisture, then the PCI has to be heated up to its reaction temperature, or the pyrolysis temperature. So, first is heating is required, then pyrolysis. When the pyrolysis take place, is volatile will come out, right, and then the product of volatile, that is the product of pyrolysis, that is this volatile has to be burned out, right, then the combustion of the pyrolysis product, and finally the combustion of the residual char, whatever you get the char, that has to be also burned. Okay. Now, it has been found there is the first 3 steps like heating, pyrolysis, and the combustion of the pyrolysis product, they take place within 0.1 second. It does not take too much time, but major time is taken by the char combustion. Combustion of the char take 1 to 4 seconds, but you must keep in mind the residence time in the raceway is not very high. It is very short duration, maybe 3-4 seconds, maximum 5 seconds, maybe less than that. So, basically the combustion of the char 1 to 4 seconds. So, if the char is not completely combusted, they makes lot of problem. So, on-board char can block the voids, coke bed are there. In the coke bed they can deposit and then block the coke voids. So, that they can do. They also can be fluidized at the top, if the, that is, they can also get fluidized and come out of the system. And they also, because these char are very reactive and they can increase the carbon gasification reaction, and as a result in the upper part of the furnace, even in the upper part, which since the reactivity is more, even at comparatively lower temperature, the carbon gasification can take place and it will increase the CO gas at the exit. So, those are the things, but major problem is that it can block the ports. That is the most important thing. If they block the ports, the permeability will be hampered both in the wet and the top zone. Secondly, to ensure char gets completely burned, following steps are taken. That is the charge, your aim will be the char get completely burned inside the raceway, right. So, for that what you have to do, the thing is that particle size should be low, because lesser the particle size, surface area increases, higher the surface area, faster is the burning. But problem is you cannot have a powdery thing, that is then its the flowability through the channel will be decreased. So, but 80% should be below the 750 micrometers, such that you have sufficient surface area for burning, okay. And very fines also cause the, that is why I think, and should be dried and powder should be separated, as I said, but the size should be less than 750 micrometer, 80% of the powder or of the fines, right, of the PCI. And it has been found that the high volatile coal are combusted better, because it has been found that the char produced from the high volatile coal, those are also very porous and very reactive. As a result, they burn faster. So, high volatile coal is good, but too much of volatile is not also good, because everywhere there is a ceiling, because optimum amount of volatile matter is required, but on the higher side. But too much high, then it will reduce the fixed carbon in the PCI. If you reduce the fixed carbon, then you may not make up the replacement ratio, okay. So, that is the another thing. And third is that low ash, always low ash coal is favored, because if you have more ash, one thing is that ash contain lot of silica. So, as a result, silicon in the hot metal will increase, because it directly goes from the raceway. There is the silica bonds to SiO gas, and SiO gas in presence of carbon converted to silica and get into the hot metal, right. That is one problem. Another problem is that if you have a large amount of the slag, then also the volume of the slag will be high, and that can cause the flooding in the wet zone. So, now, so after this PCI, so PCI you understand, and then we come to the preheated air blast, that is the blast furnace stoves. And this preheated air, as I said, preheated air means it carries some sensible heat along with it. So, if you have some sensible heat, basically you can supplement some of the heat generation by the coke. As a result, you can reduce the coke rate, obviously. So, reduce the coke rate by reducing the heat load of the coke, right. And then, so high blast preheat helps in combustion kinetics and increase the RAP. This is very important point. Blast heat, not only it reduce the coke rate, but nowadays the blast preheat is 1200 degrees centigrade is essential when you are charging the PCI. If you the hot blast, it can easily heat up the coke very quickly. It will heat up the coke, it will do the, every process will be faster, because higher the temperature, kinetics is very fast. So, coal combustion also will be facilitated if you have a preheated air, because when you charge the PCI, it is fast interacting with the hot air. So, if the hot air is, there is the, basically it is the hot air that is basically heating it up, and then its pyrolysis is taking place, and all this heating and pyrolysis all are endothermic, and it is extracting the heat from the hot air only. So, if the hot air has sufficient heat potential also, there is the higher temperature means his heat potential is high, which quickly can give the heat, and its capacity is also high. So, as a result, the blast preheat is very important. Higher the blast preheat, PCI combustion will be facilitated. Then air is preheated, And how the air is preheated, that is very important, you need to know. That is basically air is preheated in the blast furnace stoves. I will just talk about some stoves. Around 20 to 40% of the top blast furnace gas, whatever the blast furnace gas is produced, it is also rich in CO. Quite large amount of CO is there, around maybe 15 to 20% CO is there in the blast furnace gas. So a part of it, around 25 to 40%, and also blast furnace gas has sensible heat also. A lot of gas are coming at around 100 to 200 degrees centigrade, lot of sensible heat. It contains CO, so chemical heat is also there. So around 25 to 40% of the blast furnace gas is used for the heating of air blast in the blast furnace stoves, and rest of the another 60% goes for the downstream application, further downstream application. Okay, so blast furnace gas has a utility, and this blast furnace gas 40%, 25 to 40% blast furnace gas is used only for preheating the air in the blast furnace stoves. Now the stove is a tall cylindrical, this is like this, very simple. Stove is very simple. You can find a tall cylindrical part, that is, it is around height around 20 to 36 meter and diameter 6 to 8 meter, and it is the steel cell lined with insulating bricks are there. Obviously it is a furnace, so insulating brick has to be there. You can find it has two chamber, one is that combustion chamber, another is the checker brickworks. This checker brickworks means with a lot of, the brickworks is such that it has a lot of surface area. So in the first cycle, what you do in the first cycle, that is the, you burn the basically the blast furnace gas, BF gas, blast furnace gas, you burn it here by in presence of oxygen, and whatever the heat is generated, this is called the combustion chamber, and heat is generated and heat is exchanged with this checker brickworks, and because of large surface area, it easily quickly takes up the combustion heat. Okay. So it takes around, that is the thing, it takes around 2 to 4 hours for heating up. So heating up it takes little time, that is the combustion, and 2 to 4 hours for the heating up. Then the combustion stops, and after that in the next cycle, what you do, when the checker bricks is heated up, and then you pass the air through the checker bricks in the reverse cycle, air through the checker bricks, and then air get heated up by taking the heat from the checker bricks. Okay, so that is the way it done. And then it cooling, it takes around, that is the air takes around 1 to 2 hours, right, for heating of the air or cooling of the checker brickworks. So since the cooling of the checker bricks is faster than heating, a minimum of 3 stoves are required, 1 on cooling and 2 on always on heating. 2 should be on the heating and 1 is cooling, because your heating of the checker bricks require more time compared to its cooling. It first cool down very fast, but he heat it up little time. So that's why 2 remain on heating, 1 in cooling. So this is about the hot blast stoves. Okay. So the reference, lot of references we have used here. One is that Amit Chatterjee, lecture at IIT Kharagpur 2007, and then Wave, and then A.K. Vishwas, Professor Deepak Majumdar, a first course in iron making, steel making, and then another Wave, and then Ghosh Chatterjee. Okay. So what are the conclusion? One thing is the reduction in coke rate in blast furnace leads to reduction in cost and increase in the productivity. This is important. And coke rate may be reduced by better burden and its distribution. That is one thing, and we will discuss about the burden preparation and the distribution later lecture. And the coke rate can be reduced by blast additives, right? Blast additives like oil, PCI, and then steam injection will come later on, and blast preheating. And oxygen enrichment basically is used to supplement this process. Basically, I will talk about that thing. So all these blast additives are used along with the oxygen enrichment. And for PCI injection, coal should be selected with volatile metal ash and size distribution, with proper volatile matter. It should not be very high, and ash should be as low as possible, and size distribution I have said 80% should be less than 750 micrometer. And blast preheating not only reduce the coke rate, but also helpful for the PCI combustion kinetics. Okay, thank you. And then in the next lecture, I will discuss about the oxygen enrichment and the steam injection.